Hello, my name is Wendell Boucher. It's the 25th of August, 2016. The title for this presentation is Transformer Design. Capacitance referred to the primary winding. What we are going to speak about is applicable to all transformer designs that have a substantial transformer step-up turns ratio. Usually this applies to high voltage transformers, but it can also apply to low voltage transformers. For example, a converter that operates from 28 volts DC and produces 270 volts DC would incorporate a step-up transformer, yet it is considered a low voltage application. The magnitude of the capacitance, called CEP, is often rather high and does cause one to think about which converter topologies are best for the job. As an example, if we have a CEP value of, say, 0.01 microfarad, that's quite reasonable for a step-up transformer, especially in high voltage. This would raise havoc using an LLC topology. Yet the LCC topology would be a great choice since it utilizes both CEP and LLP, where LLP is the leakage inductance. So let's provide some definitions and do some calculations. What you're looking at is a cross-section of a transformer showing 3 winding layers. The first one is in brown or pink, whatever color comes out on your screen. It's different from the yellow. That's the primary, let's say. The secondary is 2 layers in yellow. And here's what's important. The length of the winding is the distance from this point to this point. A more proper name is perhaps traverse, in magnetics companies particularly, but I call it the length of the winding. The space between layers is right here, and that's called S in the equation. S for sugar. It's the spacing due to insulation. We usually put insulation in here for high voltage transformers. There's also a central line you'll note right here, and that's very important too. We'll tell you why. There are 3 conditions to meet if the linear equations we're about to show you are to yield an answer that is, say, about 15% correct. I say 15% because transformers can hardly be reproduced within 15%. The actual equation is pretty much accurate to about 1 or 2%. But here's what we must do. The ratio of LW to S is to be greater than 50. That's a ratio of this distance to this distance. Number 2, all windings are centered on each other. That means if you look at the center of this layer, it should be centered on the center line. All layers should be centered on that central line. Number 3, all winding lengths, LW, are the same. Now when we wind an actual transformer, sometimes we'll be off by a turn or 2 in that length of winding. That doesn't matter that much. That's close enough. We simply don't want you to wind, say, a primary here and a secondary that's maybe half that length of winding. If we do that, the equations are not linear anymore, and the only way to solve problems like this would be to use FEA, particularly for leakage inductance. Okay. I'm going to give you one more equation, but we're not going to be using it, but you will use it when you design an actual transformer. Explain that just a moment. CS stands for static capacitance or parallel plate capacitance, and the standard formula is just below. It's right here. CS 0.224 times the mean length of turn times the length of the winding. Both of these together is the area of the plates times the dotted constant, and all divided by the distance between the layers, which is called S in this case, and it's in picofarads. I define it a little bit more here, but let's talk about the K dielectric for a moment. This is the dielectric constants of the insulation in the space between the layers of copper. This value is about 4 for most materials, but if you're not sure, you want to check it by looking at the material specifications or measuring it. Now in this particular case, or this particular presentation, note that in the real world the static capacity between windings is seldom the same. But in this presentation we will use a fixed value of 400 picofarad between all windings to simplify the calculations. It has no effect on the accuracy of this presentation. Saves us some computational time in this presentation. Now let's do an example. I'm going to do the example and explain how it worked. First, I might show a schematic to you, like this. Where this is LLP, stands for the leakage inductance referred to the primary. LM is the magnetizing inductance. And at transformer houses, we often use expression looking into this point to ground of open OCL, or open circuit inductance, which includes both magnetizing and this, which you can clearly see. But let's remove that because that's not what we're discussing anyway. And draw another schematic for you. Here it is. Now if we were to do this, in both cases, we now have an LLC and an LCC type of converter. Now you can see that the LLC, it's a C, has no capacitor here. The LCC wants a capacitor here. And we call that capacitor, of course, CEP. That's what we're going to be talking about today. If you put that capacitor down here, I'll be very brief about this, and its value is somewhere about 0.01 or higher. It changes the characteristics of this circuit radically. The LLC designers don't want to see any capacitance down here. 200 or 300 picofarads is okay, but 1,000 picofarads up, not so good. I wanted to mention that because I did discuss it in the first page. Now we're going to start with our first example, and we do it this way. It's a coil. It's a coil, a layer if you will. If we wanted to do it very nicely, we would draw it this way. But it takes more time. That's why we don't do it that way. Okay? So let's take this layer. This is really, remember now, layer of turns looking like this. This one's another layer like that. And they're much closer together in reality, of course. But let's take this one and we'll ground it here. Ground it here. We'll put 1 volt here. Put a circle around it. And we'll put 5 volts here. This is how we start. Normally we actually start with winding we had two layers like that, we would probably say we had 500 volts here. That's 5 times this would be 2,500 volts up here. This is actually how we start to look at a transformer design, especially looking for capacitance values. But we want to scale this 500 volts down to 1 volt. We have a reason for doing that. A little later I'll tell you why. So if this is 1 volt for 500, this is going to be 5 volts for 2,500. Okay? Now let's erase this and do something else. We're going to do this. This is the voltage. This is the difference in the voltage. 0, 4. Now, how do we find the capacitance? I'm just going to do it for you. Now we're going to talk about a static capacitance. CS equals 400 picofarads. Now remember, we went up here and showed you an equation right here. That's this value. Normally you would calculate it doing this. Okay? But here we've picked a value, called it 400 puffs. I picked that because that's a rather common value in high voltage transformers. Somewhere between 75 and 500 puffs is fairly common. Otherwise it doesn't mean anything, it's just a number in our equations. So that number times 400 equals CEP. Sounds simple, doesn't it? I haven't showed you all the details yet, which is really, that number is really 16 over 3, which is, calculating it for you now on a calculator, 5.333 times 100, or times 400, I'm sorry, times 400 equals 2133 picofarads. So CEP, in our case, equals 2133 picofarads. So it's not really 400 picofarads anymore, it's 2133. It's a lot more. Now what do we actually do down here? Now I'm going to show you. To get this capacitance, CEP, we do this. We have CEP, generally speaking, and we have more layers. We would have CEP1 in this area, CEP2 in the next one, but for now it's CEP equals C multiplier, that's good enough, times CS. It's as simple as that, but what's C multiplier? CS we know, it's right here, or we can calculate as I showed you. But what's C multiplier? Well, here's what it is. C multiplier equals literally A squared plus A times B times B squared over 3, and for now we'll say V primary squared. This is V primary right here. This number is V primary. Now, the actual voltage on the V primary, as we showed you before, is about 500 volts. But if we put 500 in this equation, we have to square it. It's a lot of work. So, we make this 1. We make that equal to 1. Don't need this anymore. This becomes 1 squared, or 1. Simply disappears. So we're left with this equation. This is the equation to remember. This one. Now let's change the diagram a little bit. Instead of doing it this way, let's do another calculation. I will leave 1 where it is. We're going to change the upper one. Let's do that here. And we'll put a 5 here. We'll put, excuse me, that's not what I meant to do. I want to put a minus 5 here. This is 0. And we're going to ground this point. Makes that 0. So what do we have on this side? 0 minus 1. Minus 1. On this side we have minus 5 minus 0 is minus 5. Now, we'll call this our first example, the one we had before. And let's move this up. And we can label that number 1. It says plus 5 volts out. Okay. Now we'll do this example. Now what's changed? Well, we want a squared plus ab plus b squared, so let's look at that. What's a? It's this. What's minus 1 squared? That's equal to minus 1 squared equals 1. Minus 1 times minus 5 is 5. And finally, minus 5 squared equals 25. So it's all of this, 25, 30, 31. It's 31 divided by 3 is C multiplier times 400 is CEP. So what is that? 31 divided by 3 times 400 equals 4133 picofarad. So for number 2, CEP equals 133 picofarad. Now you can see already we have not changed the way we wound the transformer. We simply changed how we connect it. It's affected the effective capacity looking into the primary, which went from 2133 picofarad for plus 5 volt out to 4133 for minus 5 volt out. Alright, now we're going to bring up a program to show you. And here it is. Now if you take a look at this, it's really an AC generator. This is an AC analysis using LT Spice, a free program by the way. Anyone can download and use. A very good program as well. We're sweeping the frequency down here, and that frequency is a voltage which is applied at this node. Sends a current going this direction, sends a current going this direction. Now, you'll see we have parameters we can set up here. For example, L primary is 500 microhenry. And where's L primary? You don't see that. Well, it's really there. In this case, it's right here. There's a fixed L primary. Up here, it's a distributed L primary, distributed among these 10 coils. 2, 3, 4, 5, 6, 7, 8, 9, 10 coils. This is an attempt to show what's really going on in a transformer. Transformers are horribly complicated if you really looked at their actual circuits. But we can't model them because they're so complicated. So we try to simplify the behavior of this complex model. And this is only 10 coils, that's 20 coils, and 11 capacitors, that's 31 parts. To really do this transformer properly, we'd probably need about 200. But in the real world, in reality, that transformer is an infinite number of parts. We obviously can't use an infinite number of parts. So what we try to do is boil all this down to look like this model. We have one inductor, meaning the leakage inductance, another inductor, which is the magnetizing inductance. Here we call it L primary. Sometimes those words are interchanged. You can call it L primary most of the time because this leakage inductance is just a small part of it. It's only a fraction of its value in a real transformer, unless you deliberately design the leakage inductance into it to be a large value. It normally is a small one. But what we're doing today is trying to find this value. Now if we look at the impedance of this power supply by looking at this point, and we have the proper capacitor down here, so when we look at the impedance here, they should both match, at least within a couple of percent. So one of the values we needed to use was 2133 picofarads. Let's take a look at that. That's what we have right now, 2133 picofarads. I'll blow this up so you can see it. 2133 picofarads. And we're going to run this program. Okay, it's done. We're going to look at the impedance at this point. You see that's what it looks like. There's a pole and a zero of impedance. It's also a pole and zero of transmission because of the way we have it hooked up. A generator driving through a resistor, and it's a transfer function measured at this point. Now, there's only one curve there now, apparently. That's this one. Now we're going to look at this one. Click on that. They should match. Well, they're pretty close. If you take a look, that error is less than 1%. And to give you some idea what's really going on, let's expand this again. Remember 2133, I think it's over here. Well, it was 2132, that's pretty close to third place, we'll call it 2133 to remember it. I'm going to change that value to maybe 2000 picofarad. And now we're going to run it again. Here we go. Here's the answer. Now you can clearly see a difference. So this technique tells us whether we've calculated this value correctly because we're comparing it to a model that incorporates the value that we installed, which is 400p for these capacitors, the sum of those capacitors. And when we calculated using that number, we got, as we said, 2133. That's the number we should be using, 2133 picofarad. When we run it again, it comes up much better. A little error down here as well, also less than 1%. Okay. Now, look at the circuit a little closer. And what are we really doing? We're going in on the primary on the left, as we said before. Our 5 volts is appearing here. We want it to appear here as minus 5. This is what we do. We get rid of that ground symbol. We move it over here. Now we have the second circuit, which is this one. We grounded this end and grounded this end. Want to see that again? Grounded this end and grounded this end. Now the value we should be using get rid of that symbol. I want to move this over a little bit. To about here. Bring it up again for you. Okay. Let's also move this up so we can see it better. The value we should be using is 4136. I believe that's what we calculated. 4133. Well, it's close. We use 4133 then. 4133. Now what have we done? We've changed this value and we've changed the connections for which we calculated that value. So let's run it again. Now that's the impedance at this point, and we're going to show it over here for the model. They're extremely close this time. Look at this. So we have shown you that we can change this circuit and calculate the capacitance. In fact, the numbers are almost 2 to 1. Not quite, but almost. Now we're going to bring up a more sophisticated model for you. Now if you take a look at this, we haven't run anything yet. This is a model of a 4-winding transformer. Still sticking to 10 coils for the primary and each of the secondaries, of course. Doesn't look any different down here, except the values look different. And now we're going to calculate this one for you. Go back here. We'll move down the page this time. Now this model is much closer to a real high voltage transformer because it's got more windings on it. So here we go. We 1, 2, 3, and 4. I might mention the build directions in this direction. It's called build by the transformer manufacturers or designers for that matter. Now we're going to ground this. This is the primary again. We're going to put 1 volt in there. Secondary, we're going to ground this. This is how we designed it. We're going to connect this point to this point. This one to this. We have 3 secondaries in series. We're going to call, let's see, what did I have with that one? I got to look at it. Hold it for a minute. I just checked the schematic. The values we had were 4, 8, and 12. These are the voltages. If this were a kV, this would be 4 kV. You'll probably notice something else. We can scale down. As long as we scale down to 1, that equation is much simpler to use. What's the next step? We do this, remember? (12 minus 8 is 4. 8 minus 4 is 4. 4 minus 1 is 3. Over here, 8 minus 4, let's call these 0. 8 minus 4, 4. 4 minus 0 is 4. 0 minus 0 is 0. And remember, we call these A and this B. That's what these numbers are. They're all important numbers. And now, we'll call this CS1 because we have more of them. So let's identify this as CS1 equals 400 picofarad. We'll call this CS2 now. And we'll say that equals, again, 400 picofarad. And we'll call this CS3 and call it 400 picofarad again. Now we got enough information to make the calculations. So what did we do before? We had a number A squared plus A, whoops, plus A times B plus B squared over 3. Let's do the arithmetic then. 4 squared is 16. 4 times 4 is 16. 4 squared, again, is 16. All divided by 3. This is C multiplier. Now, since we have 3 of these and 3 down here, that answer is really 16. So let's change the pen for a moment here. Let's put the number 16 up here. And now let's do the next one. Change the pen color back and do the next one. Well, guess what? That's 16 too. or 16 also, I should say. I'll remove this. And let's take that first 16 and do it in red. This is very important. Call this 16. This one's 16 also because the A's and the B's are the same. Same pattern exactly. Call that 16. So what's this one? Well, this is 3 squared plus 3 times 0, which is 0, plus 0 squared, which is 0, all over 3, which simplifies to 9 over 3, which equals 3. Okay, so let's move that over in a moment. And we'll write a 3. I'm going to erase this. We don't need it. Now what do we do next? If I wasn't talking, we'd be doing this a lot quicker, of course. Hope you understand that. We have the red pen still. 16 times 400 times 400 times 400. Put a parentheses around these. Equals. Now let me do the calculations for a moment. This is 6,400. Picofarad, because these are in picofarad. Okay. This is also 6,400 picofarad. This is 1,200 picofarad. We add all of this up, we get 6,400 times 2 plus, was that number? 1,200. Equals 14,000 picofarad, which equals 0.014 microfarad. And we call that CEP. What do we call these? We call this CEP1, CEP2, CEP3. This would normally be called CS1, well it is here as a matter of fact, 2 and CS3. I'm just labeling them. And you could call this C multiplier. Okay, let me do that. I don't have to go all through it actually designing, but I'm trying to show you at least one time. This is actually CMULT 3. We fix that. And CMULT 1. Or in general, this is CMULT I clean that up again. The system is a little slow sometimes. There we go. CMULT times CS equals CEP, generally speaking. That's what we've done here. Now let's go back and look at the program. Remember this number, 0.014 microfarad. And now we fetch the program. You see I have 0.014 microfarad in there already. Now we're going to run it. Okay, it's done. And let me expand this a little bit for you. Now we look here, and we see the impedance at that point. If this is the right number, we should see the same thing. And we do. And just to show you if we have the wrong number, what happens, we've done this before, I'll do it again. Let's change that to 0.01 microfarad. And run it again. And you can clearly see they don't match. Change this back to 0.014 microfarad. Run it again. We're back to the match. Okay? So now that we have that number, when we look at a circuit, let's pick a yellow pen. Look at a circuit, looks like this. And we expect to have a CEP value down here. We just calculate this value. In fact, it was 0.014 microfarad. This is LLP. This is LM. That's where we use it. Now we do a similar thing when we calculate LLP. That'll be another one of my videos to come out relatively shortly. Once we have that, we've got these two elusive parameters. Then we can do an actual transformer design. This one's fairly easy to come up with. Now I'm going to show you the actual derivation of the equations. Here it is. I'm going to leave it on the paper long enough for you to copy it, or freeze your computer and copy it if you wish. I'm not going to explain this because this is another subject, of course, but this is how we arrived at the equation we're using. There's the first half. We bring it down a little bit more. It's the second half. And you can see we derived it through those other equations, probably arriving here. And then we equate this equation to this one. We do it right here. We solve for CP, by equating these equations. One is the energy stored in the system, the other one's stored or referred to the primary, if you will, knowing the primary voltage. And when we do that, you see these equations. Finally, we arrive at this, which is the end equation. Here's the multiplier we talked about and used. There's C static. Here's CP, which I call CEP in the presentation. In fact, here they are defined right here. Now, wrapping it up, the purpose of this presentation was to show you how to calculate this value, the value called CEP, so that we could use a model this simple when we write circuit analysis programs, or synthesis programs for that matter, to indicate the behavior of a proposed design, to calculate that behavior accurately. That's how we do it. The next paper will focus on the calculation of LLP. This will be the next paper. Okay? Now, I welcome all questions regarding this video, of course. I can be reached at via YouTube, I should say, and by email at wendell.boucher@comcast.net. This is my phone number. It can be reached this way as well. And I do live in Bristol, Virginia, in the United States. Thank you very much for watching.